Okay, here is calculus video lesson 15D. We're talking about special trig limits and limits to positive or negative infinity. So here we go. Box number 1 is all about these special trig limits that we need to have at the ready. There are 2 of them. The first one is the limit as x approaches 0 of the sine x over x. That's going to be a 1. And the reciprocal is also the same thing, right? The limit as x approaches 0 of x over sine x is also 1. So the thing to look for here is that if the argument, and the argument is the thing inside the parentheses of your sine function, and its denominator, or vice versa, are the same, we're allowed to say that they're equal to 1. Similarly, the limit as x goes to 0 of 1 minus cosine x over x is going to be a 0. So every time we see that this statement is happening, we're taking the limit as it goes to 0, we can use a 0. And similarly, every time we see these statements happening, we can make them a 1. I'll show you how they work in just a second. Okay, box 2, these are some examples of some special trig limits, and these are the easy ones. Okay, these are the easy ones, and I'll show you why. Let's say I'm looking at the limit as x goes to 0 of the sine of 8x over 8x. Well, notice how I have the highlighted argument, and it's the same for the top and the bottom. If my arguments are the same, I can automatically say that the answer is just going to be a 1, no problem. Okay. Number 2, the limit as x goes to 0 of 1 minus cosine 3x over 3x. Again, notice how I have the argument and the denominator highlighted. They are the same, so for my cosine, I get to use and say that that's going to be a 0. And similarly, number 3, x goes to 0, 4x over sine 4x. Again, if my argument and my reciprocal are the same, I can just say I'm guaranteed that that's going to be a 1. These are the easy ones. We'll do the hard ones in just a second. Okay, box 3. I've got 3 examples of tricky trig limits. So here we go. Number 1 says the limit as x approaches 0 of the sine of 3x over x. Okay, so right away I'm noticing that my arguments do not match, right? The argument here is a 3x. The denominator here is just a single x. So if they were to match, then I could apply the rule at the top of the lesson. So what I'm going to do is I'm going to figure out, okay, how do I make a 3x on the bottom? Well, if I multiply the top and the bottom by a 3, then I'm basically multiplying by a 1, and I would have a 3x on the bottom. So here's what I would get here, okay? This would give me the limit as x would go to 0 of 3 times, check out how I'm writing this, the sine of 3x over a 3x. So check out and see and convince yourself that that is the exact same thing as what I wrote above. I'm multiplying the top by 3 and the bottom by 3. Well, this is a constant, so I know I can pull it through my limit. So that's 3 times the limit as x goes to 0 of the sine of 3x over 3x. And now I'm in really good shape because this whole entire piece right here that I'm putting a big green box around, this is going to go to the number 1. So therefore, when I take the limit of this thing, I'm just going to get 3 times 1, and I get an answer of 3. That's how you do that one, okay? Tricky little trig limit there. Number 2, let's do 1 minus the cosine of 7x divided by an x. Again, similarly, if this thing and this thing match, then I know that whole entire limit as x goes to 0 is going to be a 0. So what I'm going to do is I'm going to multiply the top and the bottom by a 7 over 7. That's just a fancy 1, so I'm allowed to do that. That's going to give me the limit as x goes to 0 of 7 times 1 minus the cosine of 7x, now all divided by a 7x. So convince yourself that that's exactly the same thing as what I have above. This is a constant. We know the limit of a constant. It can just pop out because it's going to be itself. So that's just 7 times the limit as x goes to 0 of 1 minus the cosine of 7x over 7x. And I now know and can apply the rule at the top of the lesson that says that this entire piece goes to 0. So when I take this limit, I end up getting 7 times 0, and I end up with a 0 for my limit there. So those are the first 2. I've got another one coming up for you right now. Okay, here's the third example of a tricky limit. Let's take the limit as x goes to 0 of the tangent of 2x over x. So the first thing I'm going to do is I'm going to rewrite this as the limit as x goes to 0. I'm going to take the tangent of 2x and rewrite it as the sine of 2x over the cosine of 2x, and then multiply this by 1 over x, because that's like a 1 over an x right there. That's my first move that I'm going to do, okay? Then I'm going to rewrite this again as the limit as x goes to 0 of the sine of 2x over an x multiplied by a 1 over a cosine of 2x. Now you're probably saying, why would I do that? Well, this is the exact same thing. I'm just moving the denominators around because I'm multiplying everything. And the reason I'm going to do that is because now I'm going to invoke the trick. I'm just going to multiply top and bottom by 2 to get my arguments to match up. That's why I'm doing that. So this is going to give me the limit as x goes to 0 of 2 times the sine of 2x over 2x, and then times a 1 over the cosine of 2x. So convince yourself that that's the same thing. My 2 is going to pop out because it's the limit of a constant. So now I've got 2, sorry, that's 2 times the limit as x goes to 0 of the sine of 2x over 2x multiplied by 1 over the cosine of 2x. And we've just now discovered and learned that this whole entire piece, this limit, is going to shoot to 1 because of the example at the top of the lesson. So therefore, all I've got here now is, in red, excuse me, is going to be 2 times 1 times the limit as x goes to 0 of 1 over the cosine of 2x. Well, this guy I can just use direct substitution. If I put a 0 in for this, then the cosine of 2 times 0 is just, well, 0, and the cosine of 0 is worth 1. Look on the unit circle, cosine of 0 is worth 1. So now that goes to 1. So all I've got is 2 times 1 times 1, which is just the number 2. Again, a tricky limit, but it can be done. Okay, box number 4 is all about limits to plus or minus infinity. And there are 2 different kinds that we're going to talk about. On the left, polynomials. On the right, rational functions. So let's start with polynomials. The key to understanding the limits at plus or minus infinity of polynomials is remembering our end behavior. And if you had me last year, then you've seen this chart, okay? On the right-hand side here, starting up here, if my polynomial has a positive coefficient and an even degree, I'm rising to the right, rising to the left. Think of x squared. If I have a negative coefficient and an even degree, I'm going down left, down right, so think of negative x squared. Similarly, positive odd is up to the right, down to the left. Negative odd is up to the left, down to the right. Think of the cubed function. Rational functions is where it's a little bit more interesting. We call these, the way that you determine this is you figure out which part is heavy. And what I mean by the part, I'm either talking about the part on top or the part on the bottom, either the numerator or the denominator. So you're going to get one of these 3 choices here for rational functions. You're either going to get that the top is heavy, so P of x is heavy, so we call that top heavy. Q of x is heavy, we call that bottom heavy, or they're the same. And this is exactly like it was in pre-calculus. So if I have a top heavy function, then the limit as x goes to infinity is just going to be plus or minus infinity, whatever it happens to be, plus or minus infinity, depending if it's shooting up or shooting down. If it's bottom heavy, you're guaranteed that the limit as x goes to plus or minus infinity is going to be 0 because there's going to be an asymptote at y equals 0. If it's the same, then all you got to do is take the coefficients of whatever is in front of the p and whatever's in front of the q, we'll call it a and b, and divide them, and that will be your limit. So let me give you examples down below, and that will be the end of this lesson. Okay, so for part A, let's do the limit as x approaches negative infinity of some rational function. Well, first thing you got to recognize is that you're taking a limit to an infinity. Okay, it's a rational function. The degree on top and the degree on the bottom are the same. So the limit is going to be whatever the value of 1 over 2 is. So this limit is going to be a half. I take the number in front of my highest degree term and I divide them. So the limit is going to be a half as x approaches negative infinity. That's pretty easy. The limit as x approaches positive infinity of, I've got 100x squared over negative 2x cubed. This is a bottom heavy. This is a bottom heavy because of the limit on, the numerator has a degree of 2, the denominator has a degree of 3, so all we care about is bottom heavy, and in bottom heavy, we're guaranteed that the limit is going to be 0. So all we have to do is reference that. And then part C, Check it out. I've got the fourth degree on top. I've got a single degree on the bottom. This is top heavy. So if top heavy, then this is going to be either positive or negative infinity, depending on where we're shooting off to. So this one's going to be going to infinity. Those are the only three that you really have to recognize and understand whether or not it's top heavy, bottom heavy, or the same. And then recognizing in polynomials, you just use end behavior to figure it out. All right, that's the end of this lesson. So for this last one, if I want the limit as x approaches positive infinity of 3 minus 2x to the fourth over 15x plus 2, I can rearrange this and say that this is the limit as x approaches infinity of negative 2x to the fourth plus 3 over a positive 15x plus 2. So I'm writing it in standard form. And now I can see that the degree on top is a 4, the degree on the bottom is a 1. So this is a top-heavy rational function. So therefore, I only really care about the leading coefficients here. So this is going to be the limit as x approaches infinity of basically a negative 2x to the fourth over a 15x, because these are my dominant terms. These are the ones that rise the fastest. So I can cancel that and that, and I get basically negative 2x to the third over 15. So this is a negative function and odd. So if I recall what a negative and an odd looks like, it looks kind of like this. So as x's are approaching positive infinity, my function is approaching negative infinity. So the answer to this one would be negative infinity at that limit. So all we look at for rational functions is whether or not it's top heavy or bottom heavy, and then decide appropriately if it's shooting off to positive infinity or to negative infinity by using that chart that we learned about back in pre-calculus.